Hello and welcome to another video. In this video we're going to be working on max dot product of two subsequences. So here you're given two arrays, nums1 and nums2, and you want to return the maximum dot product between non-empty subsequences. A subsequence is an array which is formed from the original array by deleting some characters or none, while the positions of the rest are the same. So should be familiar with the subsequence. That part's pretty straightforward. And essentially, let's just kind of go through some of these examples. So for this first one, 2, 1, negative 2, 5. And so if you're not familiar with the dot product, normally you have two vectors with an equal amount of values, but essentially you just multiply two values of the two vectors. So for example, like you can multiply this like 2 and 3. Normally, like I said, they would have the same length, and then you would just multiply corresponding indices and add all that together. So it'd be like 2 times 3 plus 1 times 0 plus negative 2 times 6 and so on. But given these are different lengths, essentially now you can delete some elements. So you can just say like, okay, well, maybe I'll delete this element and then I'll like multiply all these. Or you can even delete most of it, right? So you can even delete like this, and then you can say like, okay, I'll just multiply the 2 times 3. The only constraint is that it has to be a non-zero subsequence. So you can't just say like, I'll just not use anything. So that's the only constraint, which is going to be a little, it's going to be important. So it says the maximum here is 18. So if you multiply, what does it say here? 3 times, let's see, 2 times negative 2 is going to be one of them. Or actually, oh, okay, never mind, actually. So they're saying you want to take 2, negative 2 from the top, and you want to take 3, negative 6. Actually, I miswrote this, so this should be like this. So if you take these two subsequences, then their dot product would be like this, right? So it'd be 6 plus 12, and you get 18. And so that's the maximum there. In the second example, so you have 3, negative 2, and then you have 2, negative 6, 7. And you want to take 3 from the first one, and you want to take 7 from the second one. So you would get 21 here. And in the third example, you have negative 1, 1. Or negative 1, negative 1. And so this one is kind of, will give us a little bit of intuition. So you could see here, actually, like the dot product, no matter what you do, if you take a subsequence, the dot product will be negative, and that's going to be important. So basically, this problem is pretty straightforward, right? Like you just have two arrays. Like let's just go back to this first example. So let's get rid of all this, and let's go back to this first example. So let's say we have 2, 1, negative 2, 5. And then you have 3, 0, 6. Essentially, all you really need to do is just try to maximize your dot product. And so you have the option of like multiplying, like let's just kind of look, right? Like let's say we start at some index here and some index here. So we have a couple options, right? And let's just kind of write those down. So A, we can multiply these two values and add them to our result. And if that's the case, then we would just move up our indices, right? So then we would just like compare these indices. We can do that. And then B, we can just ignore one of the values and move the pointer up to the next one. Right, so like we can just say like, maybe we don't want to do this, maybe we want to delete one of these, right? So this would be like the deletion. So maybe we want to delete negative 2. Or if you delete negative 2, we would just move this index up here. Or maybe we don't want to delete negative 2, maybe we want to delete 3. So then we would move this index up here, right? So essentially you just try to maximize those two things. Either take the values and multiply them, or just delete one of these, and by deleting I mean just moving the index up, and then getting like the recursive case there. So this is pretty much going to be like a pretty simple dynamic programming problem. And let's kind of like go through our states, and then we're going to see why this part is important. So for the dynamic programming, let's just write down like all our steps as usual. So we have our states. So for states, you can do this one of two ways, and I'll kind of talk about that a little bit later. But essentially, let's just write like the things that we have to have, and then we'll talk about the other part. So for the states, we have to have index 1 and index 2, right? You have to have it. You have to know like where you are in the array. Base case, And this one is also going to change regardless of regarding which solution you pick, and I'll talk about that as well. So base case, let's just say for now, either I1 or I2 is out of bounds, right? Like we just went through our stuff. Like let's say we're over here on this one, but then on the second one we're out of bounds. So we can't really take any more products, right? So if one of these is out of bounds, then we're just going to want to return. So if one of these is out of bounds, we are going to want to. Okay, there we go. Return 0 for now, and I'll talk about like the extra thing that we need to think about, right? Because we can't multiply anything else. And then the recursive case is kind of the thing I was saying up here. So we maximize take both values, get product, and add 2. And then what's going to be our like recursive state? Well, that's going to be pretty straightforward, right? So if we take both the values, we're just going to increment both indices. So we'll get the product and we'll add that to dp I1 plus 1 and I2 plus 2. That's one of the cases. B, we remove element from array 1, right? So like this would be like we are over here, let's say, and we're saying we don't want to use this 2, we're just going to remove it. So that if we want to do that, then what's going to be the dp state? So there's going to be no value there, but it's just going to be dp I1 plus 1, and then I2 is going to stay the same. And then the other case is we remove element from array 2, right? So dp I1 now is going to stay the same, and then I2 is going to move up, right? So it would be if instead of removing this element, we want to remove like the 3, and we want to move this up. And you don't want to move both of them up if you don't use them, because otherwise you're just going to like miss out on comparisons. Like let's say 2 and 6 was like our optimal solution. If we just move both of them up, we're never going to hit that. So if we choose not to get the dot product here, we can say like, okay, let's just move this up here. And then maybe we'll choose not to take it sometime later. So we'll move this up here. So we're actually going to get to this case. And we're obviously going to have like a cache as well for our base case. So let's think about the problem with that. The problem with this is if we try to maximize, and let's kind of like walk through the maximization of this solution here, and let's see the issue. So let's say we have -1, 1, or -1, -1, and then 1, 1. So when we first get to our numbers, we're going to try to maximize either taking both of them or moving one of them up, right? And remember, our base case is 0. So if we take both of them, we're going to get a negative result. And so in reality, we never really want to take a negative result, because that would make like normally, if you're trying to maximize, why would you take a negative result, right? You can just choose to pass. So let's see what happens if we pass, right? So it doesn't really matter actually like which one we move up, but let's just say we move up this one first. So let's just say we choose to pass, and then we move our index up over here. And now we are on this case. And once again, we're going to choose to pass. Like no matter what state we're in, we're always going to choose to pass. And once again, it doesn't really matter which one you move up, because eventually you're just going to go out of bounds on one of them. But basically what's going to happen here is you're going to choose to pass on the whole thing, and then you're going to return 0. Because the max, like if you just try to maximize these 3 things, the case of B or C will always be greater, and then you're always just going to end up at your base case and not take anything. And that's a problem, because they said in the problem that you actually do have to take a sequence, right? So if every single dot product, if every single combination is negative, your maximal result will actually be 0, but then you don't actually want to do that. And you want to figure out a way to like differentiate that somehow, right? Because like if you actually had a 0 here, like let's say 0 was one of the values, then this would be fine, right? Then you can actually just return the 0. And so you have to find a way to differentiate this from this case here. And there's 2 ways of doing that. One, you can add another state in your DP. So you can add another state, and that's what I originally did. You can add another state of like use the number or something. And then what would happen is in your base case, if you never use the number, you would just return -infinity. So you would return -infinity here. Or sorry, yeah, it would be -infinity, and that would ensure that like any case where you didn't use anything would give you the worst possible result, so that therefore you are guaranteed to use something. And then basically what you would do here is in this state, you would just anytime you use a number, you would put that as true, and then if you didn't use a number, you would just pass on whatever it was before, right? So if you did use a number, you would just pass that on. So you'd say like use the number, something like that. You essentially just pass that on, and that would be like a valid solution, and it's not going to take up any more space, because if you think about it, like if we have I1 and I2 and then like a Boolean, then our number of states is just I1 times I2 times 2. So like in big O, it's not going to take up any more space. So that's one way to do it, where you could just add a Boolean for like, did I use a value? And then anytime you never use anything at all, you would just return negative infinity as a base case. But the other way you could do it that I'm going to do, and I'm also going to do that for the like bottom-up solution, we will actually talk about the bottom-up solution, is we will essentially just get a min-max for all these things. And so if the max for one of these, is negative, right? So let's say the max here is negative, and then the minimum here is positive. So if this is the case, that means we know every single number in the dot product will be negative, right? Because every single number here is negative, every single number here is positive. So that's if that's the case, then the dot product will be negative. So then we'll just kind of like short circuit, and we'll just say, okay, well, we have to use one number in each. What do we want to use? So then we want to use the greatest number here, right? The greatest number, meaning the smallest negative number, and then the biggest positive number. So we're just going to check for that case, and then the other case is just the reverse of this. So if the min of this is positive and the max of this is negative, then also we will just short circuit and we'll say like, okay, let's take the biggest positive number, or actually, sorry, we're going to want to take the smallest positive number, right? Because the result's going to be negative. So if one of these is all positive numbers, like let's say we have like 1, 2, 3, 4, 5, and then all of these are negative. Like this is kind of the case we're checking for. If all of these are negative, so let's say these are like this. And we can just check this, like to check this is an O of n time. So because our solution is O of n squared, it doesn't really matter. So if this is the case, right, if this is the case or the reverse is the case, then we will basically take the smallest number here and the biggest number here, because that's going to give us the smallest, like, we're always going to get a negative dot product, but we want to have like the least negative dot product. So we'll take the 1 here and the negative 1 here. And that's how we'll like handle that case where you do take a number. And then as long as there is at least a 0 or a positive number, like as long as not every single dot product is negative, this will be fine then. Like this will work. But if you didn't do that, you either have to have that extra state or this like min-max check. And we're going to use the min-max check because we're going to use that for the bottom up as well. Okay, so now let's code up the recursive solution here. So first we're going to have that min-max check, right? So we'll say, we're also going to actually rename these because we're going to use these a lot. So we're just going to rename these to M and N, just to make it easier. Okay. And so we're going to say if max n, or I guess you can do it whatever way, right? So if max n is less than 0, meaning the biggest number in n is negative, and min m is greater than 0, so that means every single number in n is negative, every single number in m is positive. That means we're guaranteed to have like a negative dot product. Let's just return the max n, meaning the least negative value in n, right? We're going to try to minimize this essentially. And then we are going to return the min of m. So that's one of them. And then basically it's the same code, like just swapped around for these. So m, n, m, n. Right, so that kind of handles our case for a negative dot product, and now we can do like a normal solution. Like we can use this for all of our solutions. So we're gonna do the recursive, and we're also gonna do like the space optimized bottom up here because this one's a little bit simpler. It's more like a medium problem. So we're gonna have m and n is gonna be the length of these. So m and n equals length of the array m and length of the array n. Get the length. And we're going to use this for everything as well. So we're going to have our visited, and now we can just do a normal easy memoization DP of index 1, index 2, and we're going to say if index 1 or index 2 is out of bounds. So if I1 is M or I2 is M, whoops, okay. So if any one of these is true, let's return 0, and we handle the case where everything is negative by just short circuiting here, so we're not going to have the problem of, like I said, if you did this without this, then if your dot product was negative, you would return 0, and that would be a problem. Okay, so now we're going to have the caching case. So if I1, I2, and visited, return visited I1, I2. So we have the caching case. Now we just simply maximize out of the 3 options, right, that I talked about. So visited I1, I2 equals maximum of these 3 cases. I1, and this is going to be the first option. It's going to be taking both of them and actually getting the dot product. So I1 times n I2 plus dp of moving both of these indices up. So right, so I1 plus 1, I2 plus 1. Okay, now we have the other 2 cases where we just move one of them up, right? So it's going to be dp of I1 plus 1, where we don't take the dot product, or the I2 is going to stay the same here, and then we have the other solution of dp I1 and I2 plus 1. Okay, and now we will just return that. So we're going to return visited of I1 plus 1 and I2 plus 1. And there we go. Or actually, this should not be. This should just be visited I1 and I2, right? So there we go. Okay, so that's just our dp function, and then finally we're going to call it, right? And what indices do we want to start off at? 0, 0. So we want to call it, and we want to run it. Let's see what happens. Okay. So let's take a look. Okay. So you can see like it does work, but it's not super efficient. So now let's actually go through and let's think about the bottom-up solution and the optimized bottom-up solution. And then we can code up the optimized bottom-up solution, essentially. I'm just not going to code up the normal bottom-up. I'm just going to do the space-optimized bottom-up and actually figure out like an easier way to do it. So we're just going to go straight for that one right after we talk about like how to do it. Okay, so let's actually maybe take this and move it down over here. Okay, and the solution we're going to do is example 2. It's a little bit smaller. So essentially, if you think about like what our base cases should be for the bottom up, let's kind of draw out our stuff. So let's say, and also what we want to do, obviously, or not obviously, but just like for bottom up, because we're going to be using one array, like a 1D array. I'm gonna show this with a 2D array, but because we're gonna do a 1D array, we're just gonna say like we're gonna take the shorter array and use that for our space. So because in the space optimized bottom up, we are gonna have an array of 1 row and a bunch of elements. We're gonna go through this example, but we're gonna want to swap these first, essentially. So yeah, because our space optimized bottom up is going to hold like one of these, so we'd rather hold the smaller one. So essentially, we're just going to swap these 2. So our 2 arrays will be, the row will be 2, -6, 7, and then the column will be 3, -2, and we're going to get the dot product this way. And so if you think about it, so for the row, we're going to need 4 elements, and I'll kind of explain why. Let's actually draw this in different lines. Let's actually use lines. So there we go. So we're going to have 4 rows. Yeah. Okay, and we're going to have 3 columns. Not the best. Let's actually maybe like do this. Not the best drawing, but that's okay. Okay, so for our row, the values are going to be this, right? So it's going to be 2, -6, 7. So let's actually draw those to make it easier. It's going to be 2, -6, and 7. And for our column, it's going to be 3, -2. Okay. And now, so what you want to first do is you want to initialize, like, the reason we created one extra one for both of these is because if we're out of bounds on one of them, we want to be returning 0, right? Like in our memoization, if we go back, we want to be returning 0, right? If we're out of bounds, that's our base case. So that's kind of how we're representing that. So all of these out of bounds should be 0. So it's 0, 0, 0, 0, 0, 0. Okay. And so now basically, if you think about it, for like every square, what are 3 options? And let's kind of think about like where they would be. So option A is take the value at this row in this column, right? So we can actually write these down. So option A, take value at row and column, and then add dp I plus 1, j plus 1, right? Or something, whatever like index we're on, right? So if we take the value and actually get the dot product, we're going to add, like our indices are going to both move up by 1. And then the other 2 options is we have I plus 1, j, and dp I, j plus 1. So pretty much all we have to do is we're going to just go backwards, and we're just going to simply say, like, what's the biggest thing? So I plus 1, j is over here, right? Like, it would just be moving up in the row. And then j plus 1 would just be moving down here. And then if we take the value, then we have to add 1 to both the row and the column, which would be down here. So let's kind of like walk through what those would be. So for this, we actually wrote these down. So if we take the value, we'd have negative 14 plus 0. So obviously we wouldn't want to do that, right? And then the other options is either this value or this value. So either one of these is fine. So here we're going to have a 0. Okay, now we're going to go here. And then we're going to be basically the order we're going to fill this out is we're going to fill it out row by row backwards. Because to get the value, we need the value to the right and the value down. So you always want to go right to left for the bottom up DP here. Okay, so here we have 21 if we take this, right? And so we would want to take it because that would be bigger. So we either have 21 or 0 or 0. So we'd want to take 21. Okay, now here we're going to have 12 if we take it, and 0. So 12 and 0 or 0 or 0. So we're going to want to take it here. And then here we're going to have negative 18 plus 0, or we can take 12, or we can take 21. So we're obviously going to want to take 21. And so now here, we can take, so if we take the value, we'd have negative 4 plus 0, right? So it's take the value, then add dp of this, and I plus 1, j plus 1 is over here. So we're going to have negative 4 plus 0, or we can take 0, or we can take 12. So we're going to take 12. And then here, we can either take 6 plus 12, which would give us 18, right? Get the value, and then the next value is over here. Or we go right, or we go down. And so obviously we're going to want to go down. And so if you take a look, then you just return dp of 0, 0, and then that would be like the exact value we want. And so for this, essentially we made like a 2D array, but keep in mind that every single value, right, like when we're getting this value, what does it depend on? It depends on this value, and the value diagonally to the right. So if you notice, whenever you get a value, you only need to go 1 row down. So like when you're filling out this row, you're never checking here. So as soon as you are done with a row, like let's say you finish this row is no longer needed because you will never look here, right? Whenever you're filling out a row, you're only checking the row below it and the row itself. So what we're going to do instead of like making a 2D matrix here is we're actually just going to keep 1 row. And let's kind of show, let's do that for the 1 row and then we'll be done. So essentially we're just going to make 1 row and we're going to make it like 0, 0, 0 to start off. And what I did actually find is for space optimized, instead of doing, so for this one, I don't know if you can do it completely in place. Like, I don't know if you can do 1 row in place. But the thing that I found that is a little bit easier is instead of keeping 1 row, when you're going 1 row down, you just keep 2 rows. You keep your old row and you keep the new row you made. So essentially, we're going to start with this, and then we're going to be making a new row. So for the new row, we're going to make a new row here. And this is going to represent this row over here. So we're going to do like all the same kind of stuff, right? Like where do we want to go? So actually the row will be like this. Yeah. And it will initially all have zeros, but the only values we're actually going to fill out is these, right? Because we don't need to fill out these. So actually I did misdraw it a little. So it's actually going to look like this. And the only values we actually are going to fill out are these 2. And because we are only going to the right or down, we can get our values for the new row. So it's like the new row, and this is the old row maybe. We're gonna be able to check these values, right? And so we're gonna be able to go down and things like that. So essentially this value is gonna correspond to this value over here. And so we can like look at that again. So we can either get negative 14 and the value over here, which represents this value over here, same thing, right? So we wouldn't want to do that. So we'd want to have 0 here. So this 0 is going to represent this 0 here. And then for this value, we're going to either take 21 or 0 or 0, right? Because 21, it's going to be 21 and this value, which we have access to, or this value or this value. And so we're just going to want to take 21 here. And now that we filled out our new row, essentially all we do is we just make our old row equal to our new row, and then we reset our new row. So we're going to make our old row now equal to 21 here, and then we're going to reset our new row, and we're just going to reset our new row enough times to fill out this whole thing. So now this is going to be 0, and this new row now is going to represent, so we filled out this row, so this new row is now going to represent this row, and the old row is going to represent this row here. So this would be like 21, 0. Now that we do the kind of the same thing for the new row again, we only care about these two. We don't really care about this last one. So it's going to be the same thing. Like, and we're just going to keep track of like a row and a column, even though we're not making a 2D array, but we can still like have numbers for the row and a column. So here we can either take 12 and the number diagonally to the right. So it'd be 12 and this number, which would give us 12. Or we can take the number to the right, which is 0, or the number down, which is 0. So we're going to want to take 12, right? So we take 12 here, which would represent this 12 over here. And now here, we can either take negative 18 and the number over here, or we can either take 21 or 12. And so we're going to want to take 21. So we take 21, and now we are done with this row. And once again, we're just going to make our old row equal to this row here. So, and this doesn't cost us a lot of time, because when you make something equal, you just point to the same thing in memory. You're not really like, you're not like copying every element. But yeah, so this is going to be 2112 now as the old row, and then we're going to reset our new row one more time. And now our new row will represent this one up here, and the old row will represent this one up here. And yeah, I'm not entirely sure if you can do this like all in one thing, because you rely on the element to the right and the element over here. So you can't really like these could have two different values. So I think you do have to have like at least 2 rows. For problems that you only need the element to the right and the element below, the element below is just going to be like, you can just do that all in one place, all in one row. But in this one, I think 2 is probably mandatory. But anyway, let's go for the last one. So here we can either take -4, right? Negative 2 times -2. So we can take -4 and this, which would be -4, or we can take 0 or 12. And just like in this picture, take 0 or 12. So we just want to take 12. And last one here, so this would be 12, corresponds to here. And last one here, we can take 6 and 12, which would be 18, or we can take 12, or we can take 21. So we'd want to take 21. And once again, you're going to make the old row equal to the new row. It already is. And then finally, we're completely done. And now we just return the first element in the old row. So that's how you do this with 2 rows. And the key for space optimization is just like when you draw this 2D bottom up, see how far you're going down and right. And if you're only going down like 1 element or 2 or whatever, like not too many, then you can just keep that one chunk, right? So if you're going down only 1 element, you can just keep this chunk active, right? Your 2 rows. If you're going down, let's say like 5 elements, you can keep a 5 element chunk and just keep rotating old stuff out. So that's kind of like the that's how you see if you can do bottom-up space optimize. Just figure out like what's the maximum I'm actually recursing and how much do I actually need here. Okay, so now we can code up this space optimized bottom-up. So we are going to use this again. So we're going to we still want to have that thing to make sure that like if everything's negative, we want to just return the smallest element, because that's still going to be broken in our bottom-up DP if we don't have that. Okay, but now the rest we can just code up. So we are going to, so the other thing we can do actually is we want to ensure that we want to use, like I said, we want to use the smallest array for the column, right? So what we can do here in the beginning is we can just say like, if length m is, so if we're, the thing we're going to use to make the bottom of DP is n. So we want to make sure that length n is smaller than m. So we can just say like if length m is smaller than length n, we'll just swap those around, right? So we can just say like mn equals nm. So we could swap them around, and now we're ensuring that when we do the space optimized thing, like let's say, you know, since we are only keeping track of a column, if this column was like 1,000 and then we only had like 3 rows, we just want to swap that around and it would still work. So we're ensuring that for the space, we're actually using the minimum. And that's also super common for space optimized. If you're only using one dimension, just pick the smallest dimension. So now that we have that, now we should be able to just like do everything correctly, and our DP should be the minimum of these two. So we're going to say, let's just make it 0 for something in range length n plus 1, where n should be shorter than m now. So, and then essentially we're just going to loop through rows and columns and just update everything. So we're going to say for row in range of, and I think this should be m minus 1. This one. So we can check the picture here. So if this row, so here m would be 3, and we want to start at this row over here, which should be 2, right? So there's going to be this extra row that we're not using at all. So we need to start here, and then this n would be 2, and we want to start over here, which would be 1. So that's incorrect. So we're going to want to start there, and we're going to make a new row, and it's just going to be 0 for something in range n plus 1. And then we're going to go through the columns here. So every time you go to a new row, you want to make this like new row, and then we're going to make the new row, and then we're going to update our old row to be the new row like I showed before. So for column in range, n minus 1, minus 1, minus 1, new row, column, equals, and then we have our 3 options, right? So our first choice is taking the 2 values and getting the dot product. That's going to be m of row times n of column plus. So now you want to think about like where you actually go. So if we see this is the new and this is the DP, so going down to the right, we're not actually going down, we're just going into the DP and we're going 1 column to the right. And then going down is in the same column but going to DP, and going right, you're staying in this new. So that's what we're going to be using. So going down and to the right, we're not actually going down, we're just going into the DP. So that's one choice. Now going to the right is just going to be in the same exact row, and then going down is going to be in the same exact column in DP. Okay, and there we have that. And then finally, we need to say, after we go through the column, then we need to say the, why is this not tabbed correctly? There we go. So actually, also, I don't know why this is this. That should be that. And then after we're done with the column, we're essentially just going to make our DP the new row. And there we go. And then finally, we can return DP 0 here. This also doesn't look like it's tabbed correctly, which is kind of weird. Okay. Let's see. Okay, there we go. And you can see this one's super efficient. And yeah, I guess the big reason I usually don't do too many space optimized solutions, as you can see, this gets pretty lengthy, especially for difficult problems. But here it is for this one. So we have our memoization, and then we have our space optimized DP. So let's talk about the time and space for this one. So the time is going to be the same for both of them. It's just going to be m times n, right? The length of each one. And the space for the memoization is going to be m times n, because we have this visited cache. That's going to be m times n states. But for the bottom up, it's going to be O of min m times n, because we're just picking the smaller dimension and always using that to store our numbers. So yeah, that's going to be all for this one. And if you like this video, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.